second to last lecture, and it's going to be about bootstrapping mixed correlators with the goal of computing islands, for instance, for the icing model, and then we're also going to discuss other various numerical methods to speed up the bootstrap, such as hot starting and related things. So in previous lectures, we considered 4-point functions of identical scalar operators, sometimes with global symmetry, sometimes without. In this lecture, we're going to consider 4-point functions of distinct scalar operators. So with some general global symmetry. So consider some general global symmetry group G, and we have scalar operators phi, which we'll label with different indices I, just to show that the scalars are different, and each phi will be in a representation Ri. And then they will have, okay, so then we can write a 4-point function of these distinct scalars. So the first thing you do is you factor out the x dependence using conformal symmetry. And so there's kind of actual, there's somewhat of a choice of the precise x dependence you choose. This is the convention most commonly used in the Bootstrap literature. Other conventions would just differ by overall factors of u and v. But this is something to keep in mind, because sometimes different papers will use a different convention. But this is the convention we use, and is the one that most Bootstrap code uses. So this is how you factor out this x dependence. I plus delta j. Where again, these I, j, and k's are just labeling different scalars. And then you have this function g, which is the dynamical thing. So that's the thing you're trying to then study, which is a function as usual of u and v, where here we define delta ij just to be the difference between delta I and delta j. So one thing you can just first notice between the identical scalar case is that in the identical scalar case, these things would just be 1, because these exponents would be 0. Whereas now that you have distinct scalars, it's now a function of the differences between delta I and delta j and the differences between delta k and delta I. So that's something you can immediately notice. You can then take the OPE in the S channel, so in the usual ways, you take the OPE between this guy and this guy, and this allows you to expand this function g in terms of conformal blocks. So we have g, I, j, k, l, it's a function of u and v, and kind of analogous to the single correlator case, we expand it in scaling dimensions, spins, and representations. We have now 2 distinct OPE coefficients, because in one case it's the OPE of phi I with phi j. So you're going to get an operator delta LR. And then you're also going to have an OPE coefficient now coming from K and L. So you don't just get OPE coefficient squared, as you got for the single correlator case. That's one of the big differences of mixed correlators. Then, in general, you would have some tensor structure, analogous to the global symmetry case we discussed last time. And then you define this block, which, just like the single correlator case, is a function of the scaling dimension and the spin of the internal operator. But the novelty of mixed correlators is that it will also be labeled by this delta ij and delta kl. And so there's some kind of intuition of why you have these extra labels. It's related to the fact that when you write the 4-point function, these labels appear here. So that gives you some intuition of why there's going to be these extra labels. These extra labels, later on in the lecture, but it's already obvious here, it makes life a little bit more complicated. Because for the single correlator case, the block is not actually a function of the external operator scaling dimensions at all. So that means you just need to compute one block, and then that can be used no matter how you change, delta phi. But once you do mixed correlators, the block is a function of the external operator scaling dimensions. So that means if you look at different scaling dimensions, you'll have to then compute a different block. And so that's kind of a technical complication of doing mixed correlators.
So just to be sure, this little r label here, that's not just for representation.
This is for the representation. So this is the representations that would appear in the tensor product of the representations of phi and phi j. So like R is an element,
I'm just saying that you are labeling this with TRIJKL. In principle, for the same representation R, they can be more than one tensor structure.
Sure. Yeah. Yeah. So I'm not being as precise as I could be. It is conceivable indeed that for one representation you could have multiple tensor structures. This shows up in certain situations. Like sometimes they'll show up if you have both even and odd spins. There might be different tensor structures for each one. Yeah. So like in principle, there could be yet another label which could be some degeneracy corresponding to a given representation. For the simplest examples, that doesn't happen. But indeed, I've had papers where that did happen. So that's something to keep in mind. Okay. All right. So the first thing we can check now is you have the symmetry of the OPE under exchanging 1 and 2 or 3 and 4. And so when you do these exchanges, so when you exchange 1 and 2 or 3 and 4, which of course this quantity has to be invariant under because we're looking at Euclidean CFT, and so like rearranging these operators shouldn't matter. So this immediately implies some relations between this general function G. And in particular, it then implies relationships between these blocks, which we also write with G. Perhaps it's a little bit confusing, but that is the convention. So the various relations you get is you find that, so this is the original block, but now as a function of U over V, and 1 over V, this thing equals up to this -1 to the L factor, V to the delta KL over 2, and G delta L minus delta IJ delta KL. This -1 to the L factor basically comes because when you do the swapping, it changes the labels of the OP coefficient, and we want to keep some canonical labeling because that's what defines the blocks, and that's how you get a -1 to the L factor. Now this guy is just a function of regular U and V. And then finally, the other swapping says that this is the same as -1 to the L, V to the minus delta IJ over 2, G delta L, delta IJ, and then minus delta KL as a function of U and V. So these constraints capture all the various crossing constraints from the crossing group. And so this is a generalization of similar constraints that we saw in previous lectures for the single correlator case. So now how do we actually compute this mixed conformal block? Because it's going to be a little bit different from the single correlator conformal block that we discussed before. So you can immediately see from the fact that you have these extra x-dependent factors, which depend on delta IJ and delta KL, that if you were to try to compute the block using the conformal Casimir, which remember is one of the ways you compute a conformal block, so you would have to pass these x-dependent things through the conformal Casimir if you wanted to act on this G function and thus the block, and thus you're going to get dependence on delta IJ and delta KL. So that's something you know is going to happen. And so if you do this exercise, I won't show all the details, but you can define a conformal Casimir, and then you can find exact solutions in even dimensions, analogous to the single correlator case. So in the single correlator case, we discussed before how the conformal Casimir equation, which is just a certain differential equation in terms of U and V, which takes some complicated form. So I won't write it out, but like you can imagine it kind of like it's some function of U, V, derivatives of U, derivatives of V, and then delta IJ and delta KL. This is something you get by just acting with the conformal Casimir on the 4-point function. And this guy acts on this block, delta IJ, delta KL, and then it equals, well, basically some eigenvalues. And so this eigenvalue is fixed by conformal symmetry, so it's just some combination that you know. And so you can solve this equation exactly in even dimensions, and you basically get the exact same answer that you got in the single correlator case. And so you might recall that answer was a function of some quantity we called k beta of x. And so this k beta of x, so like all even dimensional blocks could be written in terms of a hypergeometric function, which is basically what this k beta of x is. So you just take the same single correlator answer and you just replace k beta of x by some slight generalization, which I will define in a moment. And so this thing is defined as, so this x beta over 2 is the exact same thing we had in the single correlator case. Again, we have a hypergeometric function. The difference now is that delta ij enters into this argument, and it enters into this argument as delta kl. And then depending on the dimension, whether or not it's two dimensions, yes?
Is IG should be something like 1, 2, or 3, 4, because IG it is a group index, right?
Sorry, ij?
Yeah, delta IG.
Well, delta ij is just, okay, delta ij is just some general index which is distinguishing between the different scalars.
Okay, they
Yeah.
are not the, okay.
Yeah, I mean, I guess I was being a little bit vague with that, but yeah, you should just think of it as delta ij as labeling the 4 different scalars. So like, delta I is the first scaling dimension, delta j is the second scaling dimension, etc. And so basically the story is that in even dimensions, your conformal block is always a combination of these k of x's, which are basically hypergeometric functions. So in particular, in 2 dimensions, it's just a product of 2 of them, like one is a function of z, one a function of z bar. In higher even dimensions, it becomes a more complicated combination. But the point is that you can just take the answer you have for the single correlator case and do this simple chain transformation, and that gives you the mixed correlator answer. But these exact formulas, as we discussed in previous lectures, they only exist in even dimension. And so if you want to bootstrap things in odd dimension, which is usually what we care about, because 3D is usually the main thing we care about, then you have to use instead the Zamolodchikov recursion relation. And so I can briefly remind you guys how that recursion relation looked. So first of all, so instead of defining blocks in terms of u and v or z and z bar, we introduced these radial variables called r and eta, which are related to z and z bar in a certain way. And then,
Shai, actually,
yes?
So the form of the Casimir differential operator is not that different in even versus odd dimension, right?
Yeah. Well,
So if
yeah.
you were to write a series expansion, is it actually difficult directly in 3 dimensions?
Well, I mean, look, in some sense, the Zamolodchikov recursion relation is an expansion.
Yeah, it's expansion, but I'm just talking about like the stupid this thing, just expanding z and z bar that powers.
I mean, it might depend what limit you want.
Right, but I'm just saying that is there really a conceptual distinction? Because the hypergeometric function, of course, we know so many properties of the function, but a priori one definition is just as a power series, and from that, if you just write the power series, is it really that qualitatively different between say 3 and 4 dimensions?
Yeah, I haven't thought about it from the power series perspective. I mean, one major difference is that in even dimensions you get double poles in delta, whereas in odd dimensions you only get single poles. And so that is one qualitative difference. And so, in fact, people have worked out a Zamolodchikov recursion relation for even dimensions. This was done, I think, by Peter Kravchuk and collaborators in unpublished work, but it's been integrated into the scalar blocks code on the Bootstrap collaboration website. And because there are double poles, it's a more complicated version of the non-even dimension.
That's for what? For some spinning correlators?
No. Just for spin 0.
Why bother? Why not just use the hypergeometric representation?
Well, I mean, I don't know. I mean, it's like, first of all, you might want to have some unified framework which uses the same expansion in all cases. And also, I don't know, there might be cases where I don't know. I mean, yeah, in principle, if you have the exact thing, that's probably fine for many purposes. I actually have encountered contexts, though, where it was useful having this R8 expansion in terms of poles.
Because originally, the Zamolodchikov recursion in 2D for Versoro, that was actually difficult to produce the power series expansion. Its computation is not feasible.
Yeah.
I was just wondering whether, in the 3D case, if you just want to directly write down the power series by directly solving the equation by brute force, whether that's actually...
Yeah, I mean, the differential operator, as you say, it's for every D, you have the differential operator, and D enters in a very simple way. And so there's certain limits of blocks where you can find analytic solutions for any D. So I think it's like, if you look at the case where Z equals Z bar, then the exact formulas are known in terms of hypergeometric functions. It's just the most general case, as far as I understand, there's not a simple answer beyond the even dimensional cases. And so, but it's possible, maybe if you thought of these hypergeometrics from the series perspective, maybe there would be some kind of relation. But there would have to be some degeneracy, because there is something special that goes on specifically in even dimensions where these poles start colliding and you get double poles. I mean, you can see that from the Zamolodchikov recursion relation, because that recursion relation is for general D, where D is not even. And you see that when D becomes even, poles start colliding. Anyways, so when D is not an even number, then you have this homological recursion relation with single poles. And basically the way it worked is the first thing is you do is you define this H. Okay, so basically you have your block. Let's make it a function of R and eta. And then you define some auxiliary function by scaling out an R to the delta dependence. So you call this thing H. And so like the reason why you do this is that this H now has a conventional power series in R. And so the way you do the recursion relation is that you first define like H infinity, which is the limit as delta goes to infinity of H. I'm not writing all the labels, but so this is what you call H infinity. This is something you could just solve directly from the Casimir equation by looking at this large delta limit. You know, it's some function of R and eta, as well as delta ij and delta kl, so you know all the various labels. And then you have recursion relation, which relates you know, H with certain spins and dimensions to H with shifted spins and dimensions such that you're multiplied by a power law. So this is all stuff we covered in previous lectures, so I won't go over it. I'm just mentioning this to say how it changes in the case of mixed correlators, which is that in that recursion relation you had these coefficients, and now they will just all be a function of delta ij and delta ki, which is perhaps not so surprising. And so, but the recursion relation otherwise is very simple.
Sorry, again, actually about different even odd dimension.
Yeah.
Isn't it true that the simplification in even dimensions is that you can express in terms of holomorphic and anti-holomorphic hypergeometric function up to some pre-factor involving z and z bar?
Indeed, yeah.
Whereas in 3D there isn't such a simple factor. There's no factorization of this.
Well, I mean, but you just can't express it in terms of hypergeometric.
No, I don't care about hypergeometric. I'm talking about
Yeah.
some holomorphic function with some simple monodromy property. A hypergeometric function and the monodromy is transformed as a two-dimensional vector.
Yeah.
So that's very simple. Generally, for the conformal block under the monodromy going around the branch cut, you don't express such simple property. So I guess in 3 dimension, I guess there probably is no way to express that in terms of some product of holomorphic and anti-holomorphic function with a simple branch structure.
Yeah, but yeah,
But
my guess
that's
is
probably
that
the distinction.
they were not. Okay, so that's all I want to say about conformal blocks. So just the story is that basically you have to compute different blocks for each delta ij, delta kl. You have the same homological recursion when D is not an even dimension. When D is an even dimension, you have an exact formula, and indeed there's even as homological recursion in that case, but it involves double poles and double.
I have a question.
Yes.
Yes. Is there any reason why do we care about more about odd dimension?
Well, that's just because I guess a lot of the CFTs that show up with condensed matter are in 3 dimensions, so it's odd
Yeah,
dimension.
but still, for 4 dimension, we don't have a very good result on conformal bootstrap, right? I mean,
Well, it depends what you mean by good. I mean, like,
Yeah,
so, like, okay, I mean, this is something I'll talk about more next week, but there's been some very interesting results on n equals 4 super Yang-Mills
okay.
in 4 dimensions. I would say beyond n equals 4 super Yang-Mills, though, indeed, there have not been such amazing results in 4D so far. So, you know, so there's some results with less supersymmetry, some 4D n equals 2 theories of which there's some nice results, kind of analogous n equals 4. But if you have no supersymmetry in 4D, indeed, the results are not so great. And this is basically just because it's how you construct CFTs. So like in 3D, you could construct CFTs using like an epsilon expansion. So you can have CFTs with no gauge group. So like they're very simple CFTs, they have very few relevant operators, and like that's why it's nice to bootstrap them, like ON models. Whereas in 4D, you can't construct CFTs in that way. The only way you can construct them is by having some kind of gauge theory and then like making it so the beta function is 0. And so that's a much more complicated procedure because like it's harder for the bootstrap to be sensitive to the gauge group, you know, because like there could be many different theories with the same global symmetry which have different gauge groups and the bootstrap can't distinguish between them. And I think this is probably related to why the non-supersymmetric bootstrap in 4D has not been so successful so far.
Okay.
But it could be. I mean, I think this is an open problem. You know,
So the answer basically is that for 4D there are the CFT they are more non-trivial, so we can't explore them very easily with the conformal bootstrap.
Yeah, in a nutshell, I would say so far. But I hope they will be in the future. You know, I don't think it's the end of the
But
story.
what if you just put in the same assumption as the icing bootstrap in 4D, let's say, assuming the Z2 symmetrical rather than operator, do you actually find anything at all?
Well, so I mean, people have done the bootstrap of the IC model as a function of D, and like you get some kind of kink, which as you go closer to 4D, it just becomes the free theory. And you know, and this is kind of matches your expectation that like.
But does this kind of nonsense actually rule out the possibility of icing-like models in the sense that it shares the same Z2 symmetry and has two rather
Well,
than
what
operators?
doesn't rule it out? Because really rule it out, you'd want to get disallowed everywhere. Whereas in
Right.
practice,
But in a reasonable domain of allowed.
I don't know if people did this study with islands. It's possible. I mean, originally people did it just with kinks. You know, that was originally by Salva et al. From like 10 years ago at this point. I think there's been some papers so far since then where they actually tried to do islands interpolating between dimensions. I think there's been various studies by Salva students.
But
And so-
when they have to interpolate, they can just do the searching for you.
Yeah, but it's useful to interpolate just to know, you know, what's happening. You know, because like you want to start with the theory, you know where it is, and then you want to see where it goes. Yeah, I mean, in principle, you could just do it directly in 4D, and indeed, you would probably rule out some large space, because the expectation is that you'd only get like a free theory. Anyway, but yeah, I'll try to discuss these issues more in the next week's lecture, which is I guess more about future stuff to do in the Bootstrap. But indeed, I think one of the big things in the future of the Bootstrap is 4 dimensions. You know, because like, especially from a perspective of a high energy theorist like us, 4 dimensions should be more interesting than 3 dimensions. And so it's kind of a pity that we've been mostly doing 3 dimensions and we've been neglecting the most interesting dimension. And so I think it's a big target for future research. Okay, anyways, so going back to the crossing equations we were writing before. So we had these crossing equations down here. And so we now want to write these crossing equations kind of directly in terms of the block expansion, which we'll do now. And so for instance, just taking 1, 3 crossing in terms of our block expansion, we get the following crossing equation. And so this looks very analogous to what we had in the previous lecture for the case of global symmetry. The main difference though, and so for simplicity I'm just writing I and j instead of phi j. So the main difference is going to be that you don't get OP coefficients squared, you get pairs of OP coefficients. And that really is the main difference. So that's something to keep in mind. This is like an L, but it's not the same as the spin L. Hopefully that is clear. Okay, so you get this tensor structure, ij, kl, v to the delta j plus k over 2. You get this mixed conformal block. And then this guy equals summing over delta L R prime, where R is the representation that appears in phi j, R prime is the one that appears in phi k phi L. So it's not phi k phi L, in phi k. Because in principle, those could be different representations. Delta L, R prime, lambda I L, so delta spin R prime, the tensor structure for this R prime, which as she said, there could indeed be multiple in principle, even for the same representation. That's an important subtlety to keep in mind. And there's delta I plus delta j over 2 delta L aj delta I L VU. So we get VU instead of UV because we've done the 1, 3 crossing. Okay, so you can now add and subtract these equations in order to rewrite the crossing equations in terms of what we called crossing functions before, which are just combinations of blocks. So this is just a rewriting, which is just useful for technical reasons. It's conceptually trivial, but let's just write down the rewriting explicitly. So we rewrite these equations. Lambda ij, lambda kl, delta So then we introduce these crossing functions, which will be defined in a moment. They are generalizations of crossing functions we had before. There's plus or minus because there's two different kinds of equations you can get by either adding or subtracting the bottom equation. Under Kj, O delta L R prime, lambda IL, O delta L R prime, Kj IL, F, Kj IL, minus plus. Okay, where these crossing functions f are defined analogously to what we had in previous lectures as follows. So f plus minus ijkl. So these are like mixed crossing functions in contrast to the single correlator ones we had in previous lectures. And so the mixed aspect is that now you have v to the delta k plus delta j over 2. And then you have a block, a mixed block no less, and then plus or minus u to the delta k plus delta j over 2, and you have a block, delta L, delta ij, delta kl, v. So this is very similar to what we had in previous lectures, which is a combination of mixed blocks. And so this function f satisfies some useful identities. These are useful because by applying these identities, you can kind of like restrict the naive number of cross equations you would originally get. So when you originally
Sorry, I'm in trouble reading. What's the difference between the two terms? Jerry, just swapping u.
okay, so this is v and that's u.
Oh, that's u. Okay, you're just swapping u.
And that's u and v. That's v and u. Yeah. So unfortunately, my u's and v's look extremely similar. So it's a little hard to see the difference, but yeah. And so basically, like the way you derive the number of cross equations is that you take this equation in terms of this f, you plug in your tensor structure, and then you take into account these three identities. So these identities are very important because otherwise you end up having extra redundant crossing equations. And if you have redundant crossing equations, you're in for trouble because you're going to just start getting disallowed points everywhere. Because you have redundancies, and so it kind of leads to numerical instabilities. So I actually know some bootstrappers. Yes?
Sir, what's the reason that you want to take this specific linear combination? Why not just work with the original one? What's
Well, I mean, it's just useful. I mean, like.
why is it? I mean, this thing you're writing now is equivalent to the thing you wrote below, right?
Wait, okay, so, sorry. This is equivalent to that.
Yes.
Yeah, but
So
I'm
why
saying.
do you bother with this rewriting?
Well,
What do
because
you gain? Like-
because in practice, when you do the bootstrap, you expand around a crossing symmetric point, and so it's now you want to have some quantity which is like a block minus the cross block, and then you expand that around z bar equals a half. And then you define functions which are basically like derivatives in terms of z and z bar of this f around z and z bar equals a half. And like those things, for like they're only non-zero for certain derivatives, etc. So it's just a convenient way of organizing. I mean, again, like there's nothing conceptually profound going on here. It's just a way of organizing, the derivative expansion for when you're computing the derivatives of blocks.
At some point, you will have to expand this tr prime in terms of tr, right?
Sorry?
At some point, you will have to express the tr prime in terms of
Yeah. So basically, what you do in practice is that you put in the explicit expressions for tr prime. This is just a bunch of numbers. It's a big tensor. And then that's going to give you a bunch of relations between the f's times these OB coefficients.
Well, you don't have to use the explicit expression of the tensor because, in principle, the representation could be very high dimensional, let's say in this situation.
Yeah.
But you don't have to put in the actual explicit tensor, which has many entries, right?
Well, okay.
As for,
Yeah, I mean, you could do something more clever if you know how this is written in terms of that, using some mathematical argument, then you could just use that relation. But I'm saying, but if you want to just be stupid, then you could just literally put in the expression for this and that, and then just look for all the equations you.
But if the representation dimension grows, the
Yeah.
stupid way is that
If it's a very high dimension thing, then you want to be more clever. You want to get, what do they call the things like braiding matrices or something like? I forget what the math.
I mean, it's essentially just like a crossing kernel, except that the group of interest is not conformal group, but the global single.
Exactly. Yeah. So such functions are known for SUN. I think they're known. They're probably known for other classical groups. Usually, I just do it by brute force just to be safe. But indeed, there can be cases where you want to be more clever. There's this book called the Bootstrap book. which is a very useful book because it has these like relations between different tensor structures for like every conceivable classical group. Unfortunately, you have to learn Bootstrap notation in order to decipher it, but it is the best reference I know of for the details of these things. So I've used it myself. I think you guys used it in some of your Bootstrap studies. Well, at least Yin used it. That's actually how I learned it. Anyways, so you have these redundancies of these f's. It's very important to take these into account because this will reduce the naive amount of cross equations you have. And if you don't use them, then you have redundant cross equations, then it leads to numerical instabilities. Okay, so now, now let's get some practical examples after we've kind of introduced the difference between mixed correlators and single correlators. So you see the main difference is that, well, you have more cross you don't get OP coefficients squared naturally. Instead, you get pairs of OP coefficients. And you have to compute blocks for every separate scaling dimension. You can't just use the same block for everything, as was the case for a single correlator. And so, but the main problem is that the fact you don't get OP coefficients squared. Because remember, a big part of our Bootstrap algorithm is the claim that we have some positive quantity, which is OP coefficient squared, times like some vector, which you could think of as derivatives of z and z bar around these cross blocks. And so how do you take into account the fact that you no longer have a quantity squared, instead you just have pairs of OP coefficients? And so the way you take that into account is that you have to consider constraints that are symmetric matrices of polynomials and not just a polynomial. And so you might recall, but before I go into the details of that, let me give you an explicit example which will kind of flesh things out. So consider a Z2 invariant C of T. For instance, when we study the Ising model. And so in this case, we define the lowest even guy as epsilon. We define the lowest odd guy as sigma. These are both scalar operators. And so, of course, only even operators can appear in the OPE of even and odd with odd, and only odd can appear in the OPE of even with odd. And so when we studied this example in previous lectures when we were doing single correlators, but in that case, we only studied sigma, 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 sigma. Although in principle, you could say we also studied epsilon, 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 because there's not really like a way of distinguishing between the two from the single correlator perspective. Now we want to study, in addition to this correlator, we want to study these other correlators. Epsilon, epsilon, sigma, sigma, and epsilon, 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 epsilon. These are the only 4-point functions of these sigmas and epsilons, because you can't have 3 sigmas and an epsilon. That's not Z2 invariant. And so in general, if your goal is to bootstrap the Ising model, the motivation for looking at the system of correlators is that it's always useful to consider all correlators of relevant scalars. Because in general, you want to look at correlators of low dimension operators, because that seems to be what affects bounds the most. So we can consider these set of 3 different 4-point functions, and then we can apply the Crossing equations to each inequivalent permutation of these 4-point functions. So in this case, there's just one permutation. You make 1 go to 3. Also, just one for this. In this case, though, there's 2 permutations, because you can either you can have this guy equal sigma epsilon epsilon sigma, or you could have sigma epsilon equals sigma epsilon sigma. Anyways, so after considering these various permutations, which again is just using the formulas above and just plugging in the fact that the tensor structure is trivial, and then just solving for the various combinations of f's, you get the following equations. So you get a sum over even spins. Here we get this OP coefficient squared. I'll write plus because this is like the plus representation. You get an F where it's just all sigmas, so this is basically a single correlator F. That's one equation. This is the equation you get from sigma, 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 sigma. So you just get one equation, the same single equation we got in the first lecture. You get a similar equation for the epsilon guy. It will also just give you the single equation. Now the OP coefficient involves epsilon, delta L plus. This also has an OP coefficient squared, so it's the kind of simple thing we know from single correlators. So no novelty so far. So this is where it gets interesting. So now we look at this guy. So we first look at the configuration where it's sigma epsilon equals sigma epsilon sigma epsilon. So in that case, we still get an OP coefficient squared, which is just the sigma epsilon OP coefficient, but now it involves the odd representation, not the even. That's why I write a minus. And in principle, this includes all spins, not just even spins. So sigma epsilon. So this is the first example of a mixed F, because the sigma and epsilon have different scaling dimensions. And then lastly, there's an equation coming from relating sigma epsilon to epsilon sigma epsilon. And there's two such equations, as we know from the formula above. Okay, so there's a term which involves just even spins. This comes from sigma epsilon. And this is in the plus representation. And then there's two such equations, so that's why I write F minus plus. L. So the two equations, either you add or you subtract, and either you have F minus or you have F plus. And then here, this is coming from epsilon sigma epsilon. So we get a minus 1 to the L so that we can define these OP coefficients in a standard way, because we want them to both be sigma epsilon. And so switching these labels gives us a minus 1 to the L. And then we have operators which appear in the minus representation. And then we have an F which is epsilon sigma epsilon. That's the 4-point function we looked at. Okay, so we see here that we have 5 equations. 1, 2, 3, and then the last one is 2 different equations. The first 3 were all expressed in terms of OP coefficient squared, so that was very similar to the single correlator case. It's the last equation which is the most interesting one, because here you do not have an OP coefficient squared. And so that means if we want to study these constraints, we're going to have to generalize our Bootstrap setup to involve matrix constraints, to take into account this guy. This guy was an OP coefficient squared. And so basically what we can do is that we can assemble these 5 equations into what's called a crossing vector. And so we can just rewrite these things in this way. So we consider this vector of OP coefficients, sigma, O delta L plus. This is the plus representation. And the other element of this vector is epsilon, O delta L plus. This is going to be multiplied by a vector of 2 by 2 matrices, which is what I call this V, delta L plus. And then there's going to be a column vector here, sigma. I won't write out the whole thing just for simplicity. And then this plus a simpler term where it's just sigma epsilon O delta L minus squared times another vector of but this is just a vector of scalar quantity. So this isn't a 2 by 2 matrix. And this is for the odd representations. And this whole thing equals 0. So this is just a rewriting of that with the following definition of V's. So this vector, it's a 5 vector. So in the odd case, it's just a vector of scalar quantities. So it's fairly simple. So it's 0, 0, F, sigma epsilon minus delta L. Then you have some minus 1 to the L's. You have F epsilon sigma epsilon minus delta L. You have F epsilon sigma epsilon. So all I'm doing is rewriting these equations in a hopefully illuminating form. So this is the 1, 5 vector, which is a vector of scalars, but then there's another 5 vector, which is for the which is for the even representation, and this is a vector of 2 by 2 matrices. So this is kind of the new thing. So this is sigma, 0, 0, 0 minus delta L. That's the first entry. Second entry is also a matrix. 0, these are all matrices. 0, 0, F, epsilon, minus delta L. Then we have a 0 matrix, which I won't write out the full thing. Then we have another 2x2 matrix which has off-diagonal terms. So this is the first interesting guy. So of course, if it was all diagonal, then there would be no need for a matrix. And so for this off-diagonal guy, we have these f's, and then finally, the last entry, also off-diagonal, and it's just the same thing, except now we have f plus. So sigma, sigma, epsilon, epsilon, and half f plus, delta L, sigma, sigma, epsilon, epsilon. Okay, so this equation here, with these v's, is equivalent to these equations. But we've rewritten it so that you can now think of it as 2x2 matrices, multiplying these column vectors, and you want these 2x2 matrices to be positive semi-definite. So we can choose a basis such that these OP coefficients are real, such that the analog of requiring that this thing be positive, because the individual OP coefficient is real, is similar to requiring that these 2x2 matrices be positive semi-definite. And that is how we're able to implement mixed correlators using the Bootstrap. And so you might recall from the previous lectures when we were describing the details of STPB, I mentioned how STPB applies to matrices of polynomials. And so the polynomial aspect has to do with the fact that you take these f's, you take derivatives around z and z bar, and then you write them as polynomials of delta. And you do this for every spin and every representation. So that was the polynomial aspect. In the single correlator case, you just needed single polynomials because you just had one constraint per OP coefficient. Now in the mixed correlator case, we need matrices of polynomials, which are precisely these matrices. So for instance, for this Z2 case, you will have a 2x2 matrix of polynomials of delta, which are given by the derivatives of around z and z bar of these f's. But we already know how to implement that with STPB, because the discussion of STPB was general enough that it applied to matrices of polynomials. Okay. Yes?
So I often hear people that do mixed for the Bootstrap say that the complexity of the computation grows very quickly into more operators, like the 3 is the most that one has been able to do. But these matrices are not very big. I mean, in SDP usually one can handle much bigger matrices. So can you comment on the actual complexity computation?
Well, okay. So there's different kinds of complexity. So for the number of cross-check equations, so one level of complexity comes from the number of cross-check equations, and the number of cross-check equations. First of all, there's 5 cross-check equations, but then the fact that these are matrices, it kind of counts as multiplying it by 4 in some sense, or maybe 3, because I guess these things are related. And so maybe this is something like 15 cross-check equations relative to the 1 cross-check equation you would have, which does make it more complicated. I think the bigger issue people probably talk about is that, I'll discuss at the end of the lecture, is that there's kind of fancier methods you can use when doing mixed correlators, which involve scanning over OP coefficients, and that is the thing which starts to proliferate once you look at many mixed correlators. And so if you were just doing the most naive Bootstrap, which is just identical to the standard correlator Bootstrap, but just with more cross-check equations, then I don't think that would be so bad. It's the other things which make it more bad.
So say, I don't know, some people think that this island maybe not will shrink to 0 size with just these 3, but if you do more, then it will further shrink. Is that, so you're saying that there's actually there's no real difficulty including some more operator like the stress tensor?
Well, it's certainly more difficult, it's more cross-check equations.
Does it really scale by, how does it scale?
Look. So as I said, there's 2 ways of complexity. One is the number of cross-check equations and the number of derivatives. That's kind of the main thing. And then there's also, if you want to be scanning over OP coefficients, which is very important, as I'm going to discuss in a moment, because that's what really shrinks your islands, then that's something which just really expands your space of parameters. And so, because now for every single value of this list of parameters, you then have to run the Bootstrap. Now, if you were to include, say, the stress tensor, that might not be so bad because you probably wouldn't have to scan over so many OP coefficients because the scaling dimension is fixed. That would probably just add a lot of cross-check equations. I don't know. It's possible people maybe are already looking into that. People have done stress tensor Bootstrap in 3D, and so I guess it's natural you could just add a few more operators and then do IC model with stress tensor. The thing though is that the question is how would that improve things? The intuition is that usually things improve by including mixed correlators of operators of low dimension. So the stress tensor does not have a low dimension, So it's not clear how much it would improve Bootstrap. And so the thing which people have done, I think it was a paper by Ning, which with David either came out or it's going to come out, where they do mixed Bootstrap for the icing model, not just with sigma and epsilon, but they include kind of like the first irrelevant operator or something like that. So yeah, I guess that's higher than the stress tensor, but at least it's a scalar. And that apparently slightly improves the island. Although I don't know if that's come out already. Anyways, I just want to make a couple comments of how like the implementation of Bootstrap changes. So remember that there's kind of three parts of these Bootstrap algorithms we've discussed in previous lectures. There's a quantity you normalize, and then there's a quantity you extremize, and then you have constraints. So constraints is what we've already discussed. You know, you're just going to have constraints for every representation, every spin, and there'll be matrix constraints in some cases. But when you're normalizing a quantity, you can't normalize a matrix. You need some scalar quantity to normalize. So for instance, when you do the scaling dimension algorithm, usually you are normalizing like a unit operator. But the unit operator you can always write as a scalar constraint. And so in particular, in the Z2 example, say this is the V for the unit operator. So it would be spin 0, dimension 0 in the even sector. And we can write this in terms of the 2x2 matrices by just contracting them with 1s. Because of course we know the OP coefficients of the unit operator can be normalized just to be 1. And so this is how you get a vector of scalars instead of a vector of matrices. So like this V00 plus is a 2x2 matrix as defined before, and then you just define the scalar quantity. And so now you have some scalar quantity you can normalize. Similarly, if you're computing bounds and OB coefficients, then you want to normalize the operator you're bounding. So for instance, when we computed bounds on CT, we were computing bounds on the stress tensor. And so in that case too, whenever you're computing bounds on stress tensor OP coefficients, you can also rewrite it as a scalar quantity, because as discussed in previous lectures, any two operators that couple with the stress tensor are related to CT in some universal way. So in particular for the Z2 example, we can define this vector, so this is going to be a scalar quantity for the stress tensor, so it has dimension 2, dimension d, spin 2, it's in the even sector, and we can define this guy, okay, so this is d squared, this is CT, d minus 1 squared, and then you contract delta sigma, delta epsilon, with the 2x2 matrix of V's defined before. So it's a 5-vector of 2x2 matrices. And this thus gives you a scalar quantity. Now, why are we motivated to contract with this thing? Because we know that the OP coefficient of any two operators coupling with the stress tensor is related to CT in some universal way, which only depends on the specific scaling dimensions, either delta sigma or delta epsilon. And so that's why we are motivated to define the scalar quantity, and then we compute bounds on the OP coefficient multiplying the scalar quantity, and then that allows us to get bounds on CT. And you can do an analogous thing if you have global symmetries to get bounds on CJ. But one thing you can't do is that if you have some matrix constraints for some just generic operator and you want to compute its OP coefficient, you would not be able to do that because you can't compute a bound on a matrix. You always have to define some scalar quantity. And so that can be kind of like a subtlety in certain cases. Okay, so far I've just discussed how to bootstrap mixed correlators, but I haven't discussed, but right now it's like very analogous to single correlators, except there's more cross-check equations. You have to compute different blocks for every value of delta ijkl, and I mentioned the subtlety of defining scalar quantities for normalizations. If you just naively do mixed correlators though, without any further assumptions, it usually does not actually improve your bounds. So in particular, for the Z2 example, if you just run the bootstrap for those 5 cross-check equations instead of the single cross-check equation, you would get the exact same bound, which in particular is the bound we saw in previous lectures, which is delta sigma versus delta epsilon, a bound that looks like this. This is the allowed region. So you would see that nothing actually improves. So things only improve once you start imposing gaps. So for instance, for the icing model, you would want to impose that delta sigma and delta epsilon are the only relevant operators in their respective sectors. And so we discussed in earlier lectures how you impose a gap on the bootstrap, which is basically you just declare that all operators in a given representation have dimension bigger than 3, because we're in 3D, and then you just insert a specific operator below that with dimension delta sigma, delta epsilon, and then you do kind of a scan over those operators. And so from this perspective, the advantage of mixed correlators is that you just have access to both delta sigma and delta epsilon. Because if you did single correlators, then you would only have access to delta epsilon in the internal operator. Because when you take the OPE of plus plus or minus minus, you always just get plus. And so the advantage of mixed correlators is that now both the plus representation and the minus representation show up in your OPEs such that you can put gaps on both. And that's really where the advantage comes from. And so that's the thing which is going to turn this into an island. But it's not just mixed correlators itself. Because so sometimes people kind of naively believe that like doing mixed correlators will automatically improve things, but it really doesn't. It's the gaps that improve things. Okay. Now there's actually more we can do. So in addition to imposing gaps, which is kind of the main thing, then you also want to ensure that there's only a well, basically that this delta sigma and delta epsilon operator are unique. Which might sound a little bit funny, but let me explain this. So when you look at the crossing equations, which we wrote in terms of these v's on the previous slide, so you would have a separate crossing equation if we look at the even sector, and if we look at the lowest dimension operator, which we call epsilon. And so we would have this crossing equation, epsilon, epsilon, epsilon. This would involve the v for delta epsilon, spin 0 in the plus sector, and then it would involve this OP coefficient. And then we would separately have another crossing equation which involves lambda squared, sigma, epsilon, sigma, times the v delta sigma, which is in the odd sector. So I'm just making the statement that included in our cross equations we have v plus and v minus, and if you look at the lowest dimension spin 0 guide, then by definition we call this epsilon or sigma. So I'm just looking at these two cross equations. If we just input these cross equations separately, then this is not as constraining as it could be, because you can actually combine these guys just by adding them into one crossing equation, lambda, sigma, sigma, epsilon, lambda, epsilon, 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 where we have these added v's. So v delta epsilon, 0 plus, plus v delta sigma, 0 minus. Then we have to do a tensor product with a 2x2 matrix, because this is a 2x2 matrix. So we want this to be a 5-vector 2x2 matrices. And then this is lambda, sigma, sigma, epsilon, lambda, epsilon, epsilon, epsilon. So why are we motivated to combine these two guys? Well, we're motivated because we claim that sigma, sigma, epsilon is the same thing as sigma, epsilon, sigma. Like basically that because they're all scalars, these things are permutation invariant. And so that's why, instead of having two separate constraints, you should just combine this into one constraint. And so this is like one thing you should just always do whenever doing mixed correlated bootstrap. It will always make the bounds more constraining. This doesn't really require any assumption. But something you can do more is that even once you've combined these two equations as one equation like this still allows for the possibility that there could be many degenerate operators called sigma and epsilon. Which, from the physical perspective, is bizarre. It's like, sigma and epsilon are some completely random numbers. Why would you have a C of t which has 5 scalar operators, all with dimension, 0.5, 1, 6, 8, 2, whatever? But the bootstrap doesn't know that, though. Bootstrap is stupid. And so you have to tell the bootstrap that these operators are unique. And this, right now, does not require that they are unique. And so if you want them to be unique, there's something further you have to do, which is you basically have to scan over the OP coefficients. So we rewrite this equation as follows. We rewrite it. So this right now, this is a 2x2 matrix constraint here. We rewrite this as a scalar constraint. Sigma, sigma, epsilon squared plus epsilon, epsilon, epsilon squared. And then this is a matrix constraint because we can contract this matrix with this 2x2 vector of theta. I'll define theta in a moment. Although it's probably obvious what it is. Okay, we have these 2x2 matrix constraints. And then we contract this with cosine theta. And so this is now a scalar constraint. So first of all, just conceptually, it should be clear why each of these steps makes the bootstrap more constraining. Because the fewer constraints you have, the easier it is to find a functional, thus the bigger your disallowed space will be. And so we started with 2 separate matrix constraints, then we went to just 1 matrix constraint, now we're just going to like 1 scalar constraint. So we're having fewer constraints, that's why the disallowed region will get bigger. And so here, the definition of this theta is just the angle between these OB coefficients. Which you can define just to be between, say, 0 and pi. And so if you have to scan over these angles by hand, but like if you were to look at the union of the allowed regions for every single value of theta, you would find that that is smaller than the allowed region you would get from this constraint. And in fact, it's much smaller. And so this is one of the ways in one of Slava and David's papers that they got a much smaller island for the IC bootstrap, was by doing this. Now, of course, the problem, though, is that it makes your space of parameters bigger. Because now, instead of doing a bootstrap in terms of delta sigma and delta epsilon, you now have 3 parameters. Delta sigma, delta epsilon, as well as this OP coefficient ratio. And so this is kind of related to what I was saying before, which is, when she was asking, well, how does the complexity of the bootstrap increase? And so I mentioned that it increases in 2 kinds of conceptually different ways. One is just the number of cross equations. The other one is the number of parameters you have to scan over. And so because it's important to scan over OB coefficients of relevant operators, if we were to do the bootstrap with more operators, not just sigma and epsilon, but say sigma prime, epsilon prime, then we would have more such relations like this, where we would want to scan over their OP, the ratio of their OP coefficients, and then the number of parameters we're scanning over would start proliferating. And then for every single value of this like huge parameter space, you then have to run the bootstrap, and like this is why things get very challenging. Okay. So now let me transition to the computer to talk about some implementation of these things. But any questions before I do that?